Good morning, one and all. Welcome to the day 12 of the workshop session. Good morning, one and all. Welcome. Good morning, one and all. Okay, sorry. Again, good morning, one and all. Today, our keynote speaker is Dr. Hideyoshi Fuji. Dr. Fuji, who is a chemi-informatician and computational chemist, acting as a member to the leading AI-driven drug discovery company, Astless Pharma, in advanced informatics and analytics wing. His main research application focuses on cutting-edge technologies such as deep learning techniques and efficient molecular design for highly accurate compound property prediction. He holds the degree of PhD in pharmaceutical sciences, which is obtained from Chiba University, Japan, and he was a pharmacist licensee in Japan. He was certified as a genius programmer and super creator under the MITOU program in 2006 and studied high-performance molecular simulations for drug discovery under Junior Research Fellowship Associate Program at RICAN between 2007 and 2009. He is currently working on the project named Melody, which is machine learning ledger orchestration for drug discovery. This project mainly aims to enhance predictive machine learning models and decentralized data of 10 pharmaceutical companies without exposing proprietary information. The project duration is from June 2019 to May 2022. He is also currently working as a chemi informatician in Informagician Research Lab, Tokyo, Japan, which is a membership-based online community. Dr. Fuji speaks languages English and Japanese. With this note, I'm happy to invite Dr. Hideyoshi Fuji to present his work.
Yeah, thank you very much, Abraham. Yeah, it's a very kind introduction. Yeah, thank you so much. And I'm very pleased to give you a lecture on chemoinformatics. Actually, I think other teachers already talked about machine learning, AI, I guess. So today I'd like to focus on chemoinformatics techniques and also drug likeness calculations. So can I share my screen? Okay, great. Wait for a moment. Good. Sorry. Okay. Okay. Can you see my screen?
Yes, Dr. Fuji.
Oh, that's fine. So today I'd like to talk about small molecule database a little bit and also drug likeness calculation. So, okay. And today's agenda is as follows. First, I'd like to talk about drug likeness, rule of 5, and also, QED calculation, which is kind of continuous value evaluation of the drug, and that can compare molecules which is more drug-like or less drug-like. And after that, I'd like to show you hands-on training using a Google Colab notebook and the Python programming. And in the end, I'd like to, explain the special offer in the end. So yeah, let's keep up listening my lecture and enjoy hands-on training. So yeah, as Abraham introduced, my name is Hideyoshi Fuji. I'm a chemoinformatician, computational chemist in a Japanese pharmaceutical company, and I created original term informagician. I explained in the next slide, but currently I'm leading AI-driven drug discovery in Japanese pharmaceutical company, Astless Pharma. And I'm doing many projects using cutting edge technologies, and also well-known computational chemistry technologies. So we use both of them and design molecules efficiently. And currently, I'm a representative of Astra's Pharma in Melody project, which is a European big consortium focusing on developing new technologies named as federated learning, which can build a machine learning together. But we don't share the raw data. Actually, we don't want to disclose our proprietary data, but this federated learning enables us to build a model by sharing our data in a privacy preserved way and improve the machine learning model. That is very exciting project. And recently, there's a post in Melody's blog in which I was interviewed and I was featured in this post. So if you have time, please click this link. Click link later when you have time. And I'm a certified super creator under the Mito program, which is a Japanese interesting, exciting program where we find, talented, like talented programmer who has a, entrepreneurship. So it was basically 15 years ago when I was maybe PhD student. Yeah, it's a long time ago, but I have a strong network with IT guys in this, under the Mito program. And I'm currently an owner of an online community called as Information Research Lab. So if you're interested, please click this link later. And this is the definition of information, which I created last year. Information is Informaticians are those who treat information like a magician and engage the audience with a presentation like a magician. So I combined informatician and magician, which is an informatician. Okay. Anyway, let's get started to learn about drug likeness, and I am not sure you know well about ADME, but so ADME is the abbreviation for absorption, distribution, metabolism, and excretion. So when you take medicine, after you take medicine, at first the medicine is dissolved in stomach, and after that it is absorbed in the intestines, and the molecules is metabolized in the liver. That is called as first pass effect. So, and after that, after the medicine, the molecule is metabolized by the enzyme in the liver. They will be distributed to organs through your blood vessel, and after that it will be reached to kidney, and it will be excreted. So this is ADME. That is a pharmacokinetics of molecules. Then So when we design molecules for a drug, when we design a drug, we need to consider these effects. So that is a kind of multi-parameter optimization. So we think about, for example, solubility and also solubility permeability to the membrane. And also we need to think about stability of molecules in order to be not to be metabolized with several enzymes, and also we need to think about toxicity. That's because it will affect to many organs. So we need to think about many kinds of parameters when we design molecules. So when you when we think about absorption, actually the molecules the molecule needs to be absorbed at first. So actually we need to think about absorption. So in that case, we need to take into account solubility. It needs to be dissolved in stomach, and also it should be absorbed in intestine. So we need to take into account permeability as well. So in the case of think about solubility and permeability, actually in the 1997 paper, this is the famous researcher Christopher Lipinski, who used to be a researcher in Pfizer. He published a paper on rule of 5, which is, I think, really famous measurements. And in this paper, actually taking account solubility and permeability in order to improve absorption. So what I want to say, is that the rule of 5 take into account solubility and permeability only. So it is measurements for drug likeness, but it didn't take into account other parameters like metabolism, excretion, and distribution. This rule of 5 focusing on just only absorption, right? So in this paper, Lipinski analyzed, their team analyzed 2,245 compounds that likely survived to enter clinical study phase 2. So in this analysis, they found that most of molecules, 90% of these molecules passed these criteria. So one is a molecular weight lower than and equal to 500, and hydrogen bond donors lower than and equal to 5. This hydrogen bond donor is the sum of OH groups and NH groups. And the hydrogen bond acceptors lower than 10, lower than and equal to 10. It is very simple. This is a sum of oxygen atoms and the nitrogen atoms in a molecule, and calculated log P is lower than and equal to 5. So these numbers are related to a multiple of 5. So they code it as a rule of 5. So which is often used in a drug discovery. So it's very easy to apply and easy to understand, easy to remember. So we often use rule of 5 to filter out molecules, which is likely to have good permeability and solubility. So, but some compounds classes that some compound classes that are substrates for biological transporters are exceptions to the rule. That's because molecules go through transporters even if they don't have this they don't have a parameter within this rule of 5. So that is an exception. Anyways, okay. So when we apply these rule of 5, we can check the drug likeness of these molecules. For example, this toriflupromazine, one of the marketed drugs, and this molecular weight is lower than 500. That is okay. And A log P, one of calculated log P, which was greater than 5. So it is, this molecule has one violation of rule of 5. And hydrogen bond donors, which mean the sum of number of OH groups and NH groups. These molecules doesn't have any OH and NHs, so it is 0. And hydrogen bond acceptors, this molecules has 2 nitrogen atoms, so it means hydrogen bond acceptor is 2, which is lower than 5. So actually, in total, this molecules has 1 violation in the rule of 5. And also, the right-hand side, this is a chlorprostixin. This is also one of a marketed drug. It has molecular weight lower than 500, and also A log P was greater than 5, as well as this molecule. And hydrogen bond donor is the number of hydrogen bond donor is 0, and hydrogen bond acceptor, the molecule has 1 nitrogen atoms. This is 1. So when we compare these molecules, these molecules has the same violation, but the same number of violations. So how we can compare the drug likeness between these molecules? So then in order to compare, so actually when we design molecules, we need to often prioritize molecules, filter out molecules in order to choose better profile molecules. So we need some continuous score for evaluating drug likeness. Then other group, actually these are also Pfizer group, and actually Andrew Hopkins. This photo is taken in 2013. That is almost 8 years ago. This is me and Andrew Hopkins, who is currently, who used to be a researcher in Pfizer, and currently he's a CEO of Excentia, AI-driven drug discovery company, very famous drug discovery company. And actually, this Nature Chemistry paper describes the chemical beauty of drugs. This is drug likeness. So in this paper, they developed a continuous drug likeness score called as QED. QED. They actually they used a desirability score, this one. So if the some molecular property is ranged from A to C, yeah, if some molecular property is within this range, they its desirability score is range from 0 to 1. And when the molecular property is the best value, has the best value, then the desirability score becomes 1. So we can set these A and A, B, C. Actually, we can set the range of A between A and C, and we need to set the best molecular property for each parameters. So they chose 8 parameters, and 4 of them are used in the rule of 5. So one is this is a molecular weight. This is A log P, lipophilicity. And this is the number of hydrogen bond donor, hydrogen bond acceptors, which was the same as the rule of 5. And they added other parameters. One is polar surface area of molecule and the number of rotatable bonds. And this one is the number of aromatic rings. And last one is the number of alerts, which is unwanted, undesirable substructures. They defined almost 100 substructures. So they count the number of substructures in a molecules, and they count these, 8 parameters for calculating drug likeness. So in this case, they analyzed actually 771 orally dosed approved drugs, and then they analyzed the distributions of the orally available drugs. For example, in the case of molecular weight, it ranges from about 150 to 900, and the best value of the molecular weight in the orally available drugs was almost 300. And they analyzed these parameters as well, and they defined this function as a desirability function, and they performed curve fitting to this distribution and calculated and extracted these hyperparameters A, B, C, D, E, and F. After that, they calculated the geometric means of these scores, and that is drug likeness score, QED. So it's very simple, and QED value is the continuous value compared to the rule of 5. Rule of 5 is the count of violations. So if you can calculate continuous values, we can compare the molecules based on the score. So yeah, as I said, they analyzed 771 orally dosed approved drugs, and they proposed a measure of drug likeness based on the concept of desirability, called a quantitative estimate of drug likeness, which is shortened as QED. Okay. So when we calculate QED, this molecules was 0.68. The QED range is from 0 to 1. So it's almost 0.7. It's yeah, very drug-like molecules. And compared to these molecules, it has a lower value, 0.58, almost 0.6. So if we use this continuous value, we can compare these molecules. This left-hand side molecule is more drug-like than the right one. So, okay. Good. So they actually, the paper of the Lipinski and also paper of the QED written by the the CEO of Excentia. Yeah, we need to extract some data set for the analysis. So we, yeah, actually in the air, yeah, in the Christopher Lipinski paper, they used actually third parties data set, but recently we can access freely available chemical databases, for example, Campbell, and we can access many kinds of data set recently. We can access, for example, zinc databases for purchasable compounds. We can access PubChem, and also we can access, for example, Campbell, which is a patent chemical database. But Campbell, in terms of Campbell, this is very useful. That's because this is a manually curated chemical database of bioactive molecules with drug-like properties. Basically, these bioactive molecules are extracted from medicinal chemistry papers. Maybe that is over the past 40 years medichem papers. So this is very useful. And this database is maintained by EBI, the European Bioinformatics Institute of European Molecular Biology Laboratory. So this was released in 2009 at first. And currently, this version becomes Campbell 28. So it basically, this database is yearly updated, and the number of data increase over years. And currently, this database has 40,000 targets, proteins, cells, such kind of targets. And it has about 2 million distinct compounds. And they have 70 million bioactive activities, and also ADME properties, toxicity, such kind of activities. And these molecules derived from 80,000 publications, and there is 170 deposited databases. So yeah, today in the hands-on session, I'd like to show you how to extract a data set from Campbell. And I can show you maybe Campbell. Yeah. Today I checked whether I can access Campbell, but unfortunately today I was able to access yesterday, but today they might in the maintenance or something. I'm not sure, but yeah, this is web page I accessed yesterday, but you can see yeah, the number of targets, yeah, as I showed, and you can browse from this button, browse all Campbell. You can see all the compounds and bioactivities, assays, such kind of things. For example, indications, diseases, and maybe I cannot access maybe. Yeah, today I think they are doing maintenance or something. And also you can download maybe uh, uh, Oracle database dump and also PostgreSQL database dumps. So if you are familiar with such kind of RDBMS, how should I say? Database system. Yeah, if you're familiar with Oracle PostgreSQL, you can download the dump from this link, and also you can install the dataset into your database. So, and also you can access the data using web services. Campbell provides a RESTful API. So if you are familiar with RESTful API as well, you can access through the API. But today, in my session, I like to use a Python library to extract Campbell data. It is very easy to use. Even if you don't know the SQL and also RESTful API, so you can access using the Python library. Okay, let's move on to the hands-on training. So I'm not sure you can access to this link, but I can send you through the Zoom comments. I can send you the link to the Google Club. Wait for a moment. Zoom. Okay. Good. So yeah, I send you the link to the Google Club. But if you see my presentation, you can click the link from my presentation slide. You can click this link. Anyway, okay. If you access this Google Club, can you see my screen? Okay. Anyway, so you can after you access this Google Club notebook, you can run it as immediately, but yeah, I recommend you to save it in your Google Drive. So yeah, I'm sorry, this is written in Japanese, but you can copy this notebook to your Google Drive. You can save the copy. So if you copy this Google notebook, so this is downloaded to your Google Drive, and you can run it in your Google Drive directory maybe. So okay, so if you can copy the Google Grab notebook, the icon it changed from GitLab icon, GitHub icon to Google Drive icon. So this icon is changed. When the icon is changed, you finish the copy of the Google Colab notebook. Okay, at first, we need to install RDKit, but RDKit officially provide Conda environment, Conda installation, Conda package for RDKit. So we need to install Conda in the Google Colab. Actually, as the default, we cannot use Conda in the Google Colab environment, but we can install this Conda Colab package. This is very useful, but I would say it is very important. It is important that you need to perform the installation first. That's because it will require a kernel restart, so which reset the variable set. So anyways, you need to run it first. So when you run this command, this cell, you need to click this button, or you can type Shift plus Enter. So I recommend you to use Shift and Enter. Then installation starts. So downloading the installation file and installing the Conda environment, Conda package, Conda software. It takes it takes 30 seconds. Then it restarts the kernel. So okay, so yeah, when the restarting finished, you can move on to the next cells, install RTKit. So you can run conda command. And when you run the bash command, you need to type exclamation mark like this. And after that, you can type a Linux command and run it in the Google Colab. So you need to type conda and option install -c conda forge rdkit. Then you can install rdkit conda package. Yeah, it installs many packages which is used in the RDKit packages. Then, yeah, finished the installation. So you can use RDKit package, RDKit Python library. So for example, this is a Python command, Python programming. You can import RDKit package Python library, and you can print RDKit version. You can check the RDKit version. Currently, this is 2021.03.2. So yeah, when you use this conda installation command, you can install the latest RDKit version. Okay, so then we'd like to start the dataset preparation for drug likeness calculation. Then today, as I said, I will use Campbell Python library, Campbell Web Resource Client library. Yeah, I set the link of this web source client, so you can check how to use the packages. But oh no, currently I can't access. It's unfortunately, yeah. Anyways, you can check how to use Campbell Web Source Client from this link. So if you are interested in how to use it, you can check later. It is the only official Python client library developed and supported by Campbell Group, so that is very useful. So when you when you install Campbell Web Resource Client Python library, you can use pip command to install the package. So you need to type exclamation mark and type this pip command, pip install Campbell Web Resource Client. Okay, successfully installed this package. And then you can use Python library to extract Campbell dataset. So at first, you need to import Campbell Web Resource Client package. So today, I use a new client class, new client function. So you need to type from Campbell Web Resource Client dot new client import new client. Then today I'd like to download a molecule dataset. So you need to type new client dot molecule, and I can set parameters. Today I extract the molecular data set, which is already marketed. So I use the filter setting like this one, max phase equal 4. The phase means a clinical phase. So when you want to extract data set, for example, which enters clinical trial phase 2, as the paper published by the Christopher Lipinski, you need to change this parameters. But in this case, max phase underscore greater than equal to 2. That means max phase has 2 and 3 and 4. So phase 2, phase 3, and phase 4. But yeah, please, I would say please check how to use Campbell Web Resource Client later. So yeah, but unfortunately today I cannot access. But you can change this parameters. But today I just only analyze max phase 4, just only marketed drugs. So you can type it like this. And you can check the extracted data. This is the many data. and the number of approved drugs was, you can check by typing length of the variable. For example, type length of approved drugs. So it has 40,035 molecules. So yeah, unfortunately, I cannot access Campbell web page, but yeah, I wanted to show you the number of drugs. I mean, yeah, you can filter out using the web interface and check the number of approved drugs max phase equal to 4 using web page, but yeah, it is very unfortunate today. So, but this is correct. 4,035 approved drugs is registered in the Cambridge data set. And after that, we need, in order to analyze using the Python, I will use pandas library. This is a data frame.
Da almıştım. Tam o sırada kim geldi?
Okay. So it's very, it takes about 6 to 7 minutes. So yeah, please type it and wait for a moment. Anyways, yeah, it's very unfortunate. Yeah, during this time, I wanted to explain the, Campbell web source web pages, but yeah, it's really unfortunate. Yeah, Campbell. So it takes 6 to 7 minutes. During this, I'd like to show you other databases. For example, maybe Sure Campbell is also maintained by EBI. So maybe I cannot access. Oh, good. Yeah, I can access Sure Campbell database. This is also maintained by EBI. This database registers just only patent chemistry, patent data set. So you can search patent data set, patent chemistry data. Yeah, actually in the drug discovery, we need to check the related patent data set in order to escape other companies' patent. So we basically we check the patent when we start new projects. So it's very useful to search a patent database. For example, when you are looking for some data sets, like, for example, this one is patent applicant is Bayer, AstraZeneca, Novartis, Genetic, or Mark, and the description chemotherapy, and so whether the patent includes the distant phosphoinositide 3 kinase or PI3 kinase. So you can check the patent, which might be related to PI3 kinase. Then you can search it by clicking this button. It takes time. Please wait for a moment. And you can also search Campbell by the substructure. So when you are interested in some scaffold structure and looking for some patent which claim the same scaffold structures, we can you can search the patent using the 2D chemical structures. Oh, good. The Google Colab is finished. Anyways, yeah, I'd like to cancel. Okay. Anyways, so it takes time. So, and also you can search with the patent number. For example, this one. This is the patent number. You can search with the patent number. If you know the patent number, you can search soon. And this patent applicant is Mark Serrano, and you can check the patent by clicking this patent number. Okay, good. So you can see the patent claims, and you can check the marker structure of this patent, and also you can download a PDF of this patent, and also you can download documented chemical structures, and you can filter out the molecules written in this patent. So you can use, for example, molecular weight and also A log P hydrogen bond donor and acceptor. They are, as I explained, they are used in the rule of 5. So basically, we often use these parameters to filter out molecules, and we can use rotator bond count, ring count, and also some. Yeah, we can remove Lipinski rule of 5 non-compliant molecules. So such kind of filter. So and then we can export these molecules based on this filter, and after that, from this my export, we can download the CSV XML file. So it includes a SMILES string of extracted molecules. So then you can analyze the data set after you download this data set. Anyways, let's go back to the Google Colab notebook. Then it took 3 minutes. It took about 4 minutes when I convert this this data set to pandas data frame. So you can use this data frame. So for example, we can check the head of this data frame by running this command. So it includes many kinds of data. For example, it includes indication class, disease class. This molecule is related to antibacterial disease, antibacterial indication. and it includes molecular properties, which includes A log P, the number of aromatic rings, such kind of things. And it has molecular structures, which includes canonical smiles, and also CTAP, which is molecular format, and molecular synonyms, the name of the drugs, synonyms, and molecule type, small molecule, or maybe biomolecule types, maybe. And there's a flag about orally available drugs or not, and also natural product or not, and the parenteral flag or not, such kind of things. So there are many data, and also there's a registered year, this one, first approval year. So today I'd like to use this first approval year data and molecular properties data to calculate rule of 5. And also we will use later molecular structures data. So today I'd like to extract just only orally available drugs. So I use this filter, oral, this one, oral flag, this one, oral flag equal to true. And also I'd like to extract molecular properties data set. So actually they include sometimes null data. So in order to remove the null data set, so I use this filter not null function, and I extracted just only orally available data set. And the number of the oral drugs is 1700s, right? Okay. And also we can check this property, molecular properties from this data set. So it includes, for example, so I'm just showing you just only molecules, just one molecule, and it includes A log P, the number of aromatic rings, log P log D, and molecular formula, molecular weight, hydrogen bond acceptor, but and also it includes hydrogen bond acceptor based on the Lipinski rules. That is very simple hydrogen bond acceptor. That means the number of NOHs and also the number of OHs. And hydrogen bond donor, and this is the hydrogen bond donor based on Lipinski rules. That is the sum of nitrogen atoms and oxygen atoms. In the heavy atoms, molecular weight of free base and monoisotopic, and it includes the number of Lipinski rule of 5 violations, and also a polar surface area, and it includes also QED value, and it includes rotatable bonds, the number of rotatable bonds. So today, in order to calculate the number of violation of rule of 5, we would like to use A log P and molecular weight, this one, and also hydrogen bond donor and acceptors, maybe. Anyway, yeah, please run these cells to extract, the A log P, molecular weight, such kind of data set. Yeah, I just checking the whether I can extract A log P. So yeah, when we need to extract just only A log P, in this case, actually, if you type just only this molecular properties, it includes this kind of data set. This is a Python's dictionary format. So we need to apply this lambda function to extract just only just only A log P. I use the keyword of A log P. So it means, for example, when just only use one row. So this is a dictionary data format. So in this case, I can extract, for example, A log P by using this keyword, right? Yeah, 1.78. I can extract just only this A log P data. So in order to extract the whole data set from the data frame, pandas data frame, we need to apply lambda function x and x bracket, and you need to define the keyword of the dictionary format. Sorry, this is lambda. Okay. Okay. So when you need to extract this one, for example, molecular weight free base, you need to change this keyword A log P to molecular weight free base, and also this molecular weight, the type of this value is actually string. That's because this includes a single quotation. So we need to convert this string to a float value, and we need to extract year data, and I just extracted the number of violations of rule of 5, this one, Lipinski rule of 5. So in this case, this does not include a single quotation. So it means this is an integer value. So we don't need to convert this value to integer. This is just integer type. So anyway, you can run it. Yeah, you can extract molecular weight, year, and the rule of 5, and you can set a data frame of these year and the rule of 5. And actually, in this year type was the float value. I set the integer type to this data frame. Then, as you can see, we just extract the year and a rule of 5, the number of violation of the rule of 5. Then you can visualize. You can visualize the data of the trend in the number of rule of 5 violations. So when you create a graph in the Python, there is very useful Python libraries for the data visualization. Yeah, for example, there's popular one is matplotlib, and other one is plotly. And also today I'm using bokeh library for data visualization. That is very useful. Actually, in today's limited time, I don't explain the detail so much. So yeah, please check the details later, but I can explain briefly. So today I'm using For example, I'm using the year range from 1981 to 2021, and I just calculated, I just extract the number of violation. For example, in this data set, there is actually, so, we are using 4 parameters: molecular weight, log P, and hydrogen bond donor and acceptors. So there's, at the maximum, there's 4 violations. So I just extracted violation 0, 1, 2, 3, and 4. And I calculated the percentages of the number of violations in each year by calculating by calculating the ratio, the distribution. So yeah, anyway, it is easy to understand when you run this command and see the graph. So yeah, please run it by clicking this button or type the shift and enter. Okay, this is a graph created by this bouquet library. So as you can see, I'm showing you data from 1981 to 2020. And in each year, I calculated the percentage of the number of rule of 5 violations. For example, in 1981, the percentage of the violation, the molecules which has the violation, no violations, that was 66.7%. And in terms of the molecules which have just only one rule of 5 violation, the percentage of marketed drugs launched in 1981 was 23.8, and this one is the molecules which has 2 violations. So in the Lipinski's paper, they described that at least 90% of marketed drugs was at least at the maximum they have 1 violations. So it means the most of compounds, most of marketed drugs has no violations or just only 1 violation. So 10% of the marketed drugs has the over 2 violations. So as you can see, so in each year, if you sum these blue bar and this green bar, as you can see, it's almost 90%. And also, as you can see, this is over 90%. And this year, 1984, it has 100%, were 100% of market drugs were has the violation, no violation or just 1 violation. And after that, after 2000, this one, 2001, basically this is no violation. Percent of compounds which has no violations was 70%. So, but the next one, this is 2 violations. So 30% of marketed drugs has 2 violations. So I think Lipinski's Rule of 5 paper published in 1997. So basically, we often use the rule of 5 in order to prioritize molecules and filter out molecules. So it affects these trends, but recently, actually, drug targets becomes more challenging. So we need to take into account molecules which is beyond rule of 5. So I guess recent trends might be the decreasing, I guess, as you can see. So after the 2007, it was basically it's just 42% of compounds has no violations, and 21% of compounds has just only one violation. So yeah, I'm not sure the actual reason, but the trends of this number of violations is changing from 2006 to 2007, I guess. So okay, and also we can check the trends in QED. So QED is as I explained, QED is a continuous value. You can check the trends of the QED. And so in this cell, I just extracted QED values from the data set extracted by Campbell Web Resource packages. So I used this one, QED weighted. Then as you can see, this QED weighted value is string type. I need to change the string type to float value. Okay. So in this cell, I just extracted QED values from this data frame, DF oral drugs, and I extracted year and QED value, and I set up, I changed the type of each data, year and QED. In the case of year, I just convert the type to integer and QED to float format, float type. So okay, you can see I just extracted these data set year and QED, and also I used bokeh library to visualize the data. So yeah, please run this command to show this graph. Okay, in this case, I didn't limit the year range. In this case, I used the old data set from 1939 to 2020. So, and this this circle is the average of each year, average QED of each year. And this line shows the standard deviation of QED values in each year. And it's difficult to say, but in recent 10 years, maybe the average of QED might be decreasing, but actually in this era, I think the QED average of the QED value range from 0.6 to 0.8, And recent 10 years, it ranges from 0.4 to 0.6. So yeah, it's increasing. It's decreasing. Okay, so yeah, it is very good to visualize data set to understand the trends or understand some, comparing the past data set and recent data set. So it is very important when you start some project using, for example, machine learning or deep learning. So it is very important to check the data set beforehand, right? Okay, so let's move on to the next topic. Today, I'd like to try to create your own desirability score, QED drug likeness. So yeah, that is very interesting to create your own score. So at first, we need to extract SMILES string in order to calculate each molecular weight, log P or something like that. So in this case, there was other data, other column in the extracted orally available drugs data frames. Oh, sorry, I need to use head function. All right, head function just shows the first five rows, so it is very useful. Then this data frame includes molecular structure column. So in order to extract a SMILES string, we will use this column. Okay. So we need to set this keyword, column name, molecular structures, and some data does not include molecular structure data. So I remove the null data from that. So yeah, if you want to check the null data, whether it includes null data or not, you can check like that. Molecule structures is no sorry, is null function is null. No, it doesn't have. Sorry, it might be equal null. None. Sorry, it has none. Molecules are structures. Sorry, structures. And the DF oral thorax bracket. Or something long, NP, no. Okay, good. So there's a function is null, and I just extracted data in which molecular structure is null. So you can see, oh sorry, as you can see, oops. So okay, good. Yeah, this one, molecular structure doesn't have data about SMILES string. So in order to drop this data set, I used drop NA function, right? So I just extracted a data set which includes molecular structure data. After that, you can extract canonical SMILES using this function. So you can see, as you can see, if you type a canonical SMILES variable name, you can check this SMILES string. So in this case, I was able to extract 16, almost 1700 data set. Okay. Okay, so we would like to we would like to use the RDKit in order to calculate molecular properties of these molecular structures. So today I'd like to use RDKit. Then so from the RDKit package, we need to import chem module, and we need to convert by chem.mol from SMILES function from SMILES string to molecular object. For example, canonical SMILES, so one of the canonical SMILES data set, it includes this string, SMILES string, and you can copy with this one, this icon, you can copy. And if you type from RDKit import chem and chem.mol from SMILES and paste the string, oh sorry, you need to type double quotation or single quotation and copy the SMILES string. And the outputted data is a molecular object. So currently I didn't import the depiction module. So when you want to depict this molecule, you need to import rdkit.chem draw import IPython console. Then when you type this molecule object, you can draw the molecule like this. Okay, you can check the compound structure using this draw module and IPython console. All right, so in order to convert a SMILES string in parallel in the same time, I'd like to I'd like to convert the whole SMILES string list. So I use this list brackets and also loop, for loop syntax for loop, and then you know, if you type for x in canonical SMILES, you can loop over the SMILES list. For example, for x in canonical SMILES, this is a repeatable object. This is a repeatable object. So when you type this x variable, you can loop, you can print repeatedly like this, right? And if you type it in the list bracket and type, for example, X and bracket, close the bracket. In this case, you can create the list object like this. So it's very long. Sorry. You can type like this. Oops. Okay, it start with bracket. So it is a list object. So when you would like to use any functions, so in this case, we need to convert SMILES string to molecular object. So I use chem.mol from SMILES bracket and close the bracket. So in this case, you can loop this function and create the list of the mol object. So in this cell, so that is what I'm doing. So in this case, we are creating mol object list of mol objects, and then insert it into the moles variables. Okay, so good. So you can check moles, for example, index 0, and you can draw the structure like this. Okay. And in the next cell, this one, this display molecules, I will use mol to grid image function to display molecules simultaneously. So in this case, I just only displayed the last 12 molecules, and I set this parameters moles per row equal 4, and the image size is width is 400 and height is 400, and you can run it and display molecules like this. So as you can see, moles per row is the number of rows in this image, and each image size is 400 by 400, right? Okay, so as you can see, some mole objects contains multiple molecules. For example, this would be the maybe solvent or some and also duplicated molecules, molecular structures, and sometimes it includes metal ions. So when we start the analysis of molecules or doing machine learning, we need to standardize molecules. That is very important process before the operations like analysis, machine learning, such kind of things. So this is very important process, standardize chemical structures. So today I'm using the RDKit module to standardize molecules. So it is very easy. In this case, I used a large fragment chooser and uncharger. So for example, in this case, this includes water molecules. And in this case, it is very small, but it is maybe bromine and metal ions. So in this case, we often use largest fragment chooser in order to select the largest one. So sometimes if when you when you analyze the very small molecules, sometimes metal ions becomes the largest one. So in such case, we need to check in detail. But when we perform the many kinds of molecules, I often use this large fragment chooser for simplicity. And also, as you can see, this molecules has a negative charge oxygen. So yeah, it's depending on the situation of the analysis, but we basically use uncharger to neutralize these kind of molecules, right? And so this largent fragment chooser class, at first you need to create instance of this class, and uncharger as well. You need to create instance of this class, and after that, yeah, we will use this list and the for loop to calculate fragment chooser, to apply fragment chooser and uncharger in this loop. And after this, you can see running uncharger, removed negative charge, such kind of things, right? And then you can visualize these molecules. All right. So as you can see, since I used the largest fragment chooser, duplicated component was removed, right? And removed the solvent and also metal ions. And also in this molecules was neutralized, as you can see. This oxygen atom became OH groups, right? Okay. And also, yeah, I'd like to, I'd like to say that basically I often remove these duplicates. So before we standardize this molecule, these molecules, they had different metal ions, potassium, magnesium, calcium, and also the number of components were different. So after this standardization, we often remove these kind of duplicates. But in this workshop, for the simplicity, I don't do the such I don't remove the duplicate molecules. But yeah, it would be better to duplicate. It would be better to remove these kind of duplicates in the data preparation. All right. So next, I'd like to calculate QED drug likeness. So we need to calculate descriptors, molecular descriptors used in QED. And you can, as you can see, we can calculate molecular weight, log P, the number of hydrogen bond donors, hydrogen bond acceptors, and polar surface area. This is a topological polar surface area, and the number of rotatable bonds, and the number of aromatic rings. So it's very easy to calculate these kind of molecular descriptors. And then the last one is custom alert. So it's not simple, but it's, yeah, you can calculate the number of custom alerts using RDKit package. Then in this paper, they are providing molecular substructures, smart string, in the supplemental data. Supplemental. So this is a QED paper of the nature chemistry, but as you can see, sorry, there is supplemental data set. Sorry, I can't find this one, full text. Okay, there is a supplementary materials, and they provide smart string, this one, unwanted groups. So if you download this file, you can see the list of unwanted groups. So in this Google Club notebook, I download this unwanted group dataset using wget command. So you can download it into this Google Cloud platform, and also you can check the whether you download or not. So if the download is completed, you can check this file. So if you double click this button, this file, you can see the list of smart string unwanted group smart strings, right? So there are maybe 100 to 13 unwanted substructures defined in this QED calculations, right? For example, this one is the list of many, it is not inorganic atom, maybe this kind of data. All right, okay, so you can close this file. Okay, right, so so that download is completed. So you can convert this smart string into the RDKit object using chem.mol from smarts, and you need to set smart string in this function. So I'm using a for loop to create chemical mol object from smarts. So that is a kind of substructure pattern object. Then in order to calculate the number of alerts, I just created this function, calculate num alerts, and this is a mol object, right? So in order to check the whether the molecule has substructure or not, so we can use this function, mol object dot has substructure match. Then I can calculate the sum, the total number of alerts hits, right? All right, so you can run it and define the this function, but unfortunately in this RDKit library, it cannot convert to a smart string. So in this case, I guess this smart string has multiple components with this dot string. So in this original paper, they are using Pipeline Pilot, other software. So they didn't use RDKit. So there's actually a software difference yeah, due to the difference between software, between software. So actually today we are using RDKit, and RDKit cannot convert to smart string of 113 unwanted smart strings. But yeah, today I just use the rest of unwanted groups. All right. So, and then I define this function. So I apply this function to all the molecular objects and calculate the sum of alerts. So you can check, for example, alert the first alert of the first molecules. So yeah, so some molecule has 2 alerts, some molecule has 1 alert, like this, and also some molecule has 4 alerts, right? Okay, good. So next one is plotting histogram of each descriptor. So I also used bouquet library to plot the histogram, and also in order to calculate the histogram of each descriptors like molecular weight, log p, hydrogen bond donor, acceptors, polar surface area, the number of rotatable bond, the number of aromatic rings, the number of structure alerts. So these 8 parameters were used in QED calculations, and also yeah, when I calculate histogram, I used other library, NumPy library. This is very also useful and popular one to calculate some mathematic calculations. So in this case, I used a histogram NumPy dot histogram function. So let's visualize the distribution of these molecular descriptors. Okay, so as you can see, these distribution of each molecular descriptors of orally available drugs. So I think as same as the original paper, the best most frequent molecular weight would be 300 to 400, maybe 1, 2, 3, 3 to 4, yeah, 300. And in terms of log p, actually, this log p calculation might be different from the original paper. So yeah, I would say there are many algorithms to calculate lipophilicity. So in this case, RDKit calculate mole log p, but in the original paper, they used C log p, maybe in the pipeline pilot, I guess. So the distribution is range from minus 10 to 10. Yeah, some molecule has minus 20, but this is a hydrogen bond donor distribution, and this one is the number of hydrogen bond acceptor. This is the polar surface area, topological polar surface area, and this is a number of rotatable bonds. Yeah, some molecule has many rotatable bonds. Yeah, and this is a number of aromatic rings, and this is a number of structural alerts, such kind of things. I think these are very similar to the original paper. Original paper's distribution is like this. Do you know? Yeah, this is the molecular weight, the best the most frequent molecular weight is range from 300 to 200 to 400. Yeah, it's almost 300. A log P range from -8 to 10. Hydrogen bond donor and acceptor is like this. And the polar surface areas distribution is like this. And this is a rotator bond. And this is the number of aromatic rings. And this is a number of unwanted substructures, right? So almost the same distribution, right? Good. So and then I used this function, asymmetric double sigmoidal function, as the desirability function. This is used in the original paper, and you can check what kind of functions interactively using this IPy widgets and matplotlib plot library. So after you run this command, oh, there's a mistake. Sorry, there's a mistake. So please remove this bracket in this line, b equal bracket 0 comma 1000 bracket, but you need to close bracket in this after this number 1. Sorry, I will improve. I will correct this one later. But okay, if you correct this one, you can type it. And you can interactively change these parameters A, B, C, D, E, F in this formula, A, B, C, D, E, F, and you can check these change interactively, right? And this X max is the range of the X-axis. So if you change the X max parameter, you can change the range of this graph. And if you see the formula, if you change A and B parameters, this desirability score increase. So if you change this B parameter, the range of y-axis changes, as you can see. And if you change this C parameters, the most frequent point is changing, right? If you increase the C value, the most frequent point increase as well, right? And if you change D parameter, it changes y-axis, but some, yeah. Actually, this D variable change this left-hand side graph, maybe. And if you change this E and F, it will change the curvature of the left-hand side. So it would be better to decrease the X range, the max over X range. So if you decrease, if you decrease the E value, the curvature changes. And if you increase the E value, it's kind of rounded rounded curvature. And also, if you change the f value, it will change the right-hand side curvature. Right, so you can understand how these parameters affect this graph. So it is very useful to use this interactive function. Anyways, we need to perform curve fitting to histogram of each molecular descriptors. So I will save parameters and this d maximum value of the desirability function of each descriptor. So I just created a dictionary type of variable. Then, for example, in terms of molecular weight, I used SciPy library. So in order to perform curve fitting, I used this function curve fit, curve underscore fit function of this SciPy library. And in this curve fitting function, actually we need to set the initial value, this one P0, initial value of, this is a variable A, B, C, D, E, F of the sigmoidal function, this desirability function, this one. So if you set the values far from the optimum variable, it will fail. For example, if I type OI, it will be good. So sometimes it fails. So actually, this curve fitting function optimized the best parameters of A, B, C, and D, A, B, C, D, and E, and F. So in this case, this orange graph shows the optimized fitted curve fitting graph. So, and then after the curve fitting, I can extract the variables A to F. So in this case, as you know, as you can see, this function, the first return value is the parameters of this curve fitting value, curve fitting graph. So I will save it to the this parameter variable, dictionary type of this variable. This one, popT. You can see popT includes the A parameter B, C, D, E, and F, right? So I will save it to this variable, and also in this graph, as you can see, the maximum value is about 300. So desirability score range from 0 to 1. I need to save the maximum value. I will divide the score by this maximum value in order to normalize the desirability score from 0 to 1. So I save the maximum value to this dmax variable. So actually this is very limited time, so I don't explain the detail, but this is the initial value I found. So I guess if change, in this case, I use A, B variables, 1000 to the B variable, but So this one, if these initial values are far from the optimum value, this curve fitting fails. And so the default value of this max fab parameter, that is kind of number of cycles to optimize curve fitting. So you can increase the max fab equal, for example, 10,000. So in this case, it find the optimum curve fitting parameters. So you can change max fab values, or you can find the better parameters using this interactive plot. You can find the interactively the most similar values to the optimum one, right? And I will save it to this parameter dictionary variable, and also we need to perform curve fitting to hydrogen bond donor like this, and save it to parameter variable, and also hydrogen bond acceptors like this, and save it to this parameter and the Dmax, and polar surface area is like this, okay, and save it to the parameter and the Dmax variables. And in terms of rotatable bonds, this curve fitting is like this, right? And save it to the parameter and the Dmax variables, and also curve fitting about the aromatic rings is like this, right? And save it to the optimum parameters to this variable. And also last one is the number of structural alert, like this, okay? And save it to the parameters variables. Okay, so yeah, we finished the we finished the curve fitting to of the 8 parameters, and save it to the parameter variables. So it is a dictionary type. So for example, you can see in terms of alert, a custom alert, you can use these variable parameter A, parameter B, C, D, E, and F of the desirability function. And also I save it to Dmax. There is, okay. I might miss the molecular weight, maybe 1, 2, 3, 4, 5, 6, 7. Sorry, so I missed to save the molecular weight. So yeah, this one. Okay, good. Right. Okay, so this one, molecular weight. So there is 8 keywords alert, 1, 2, 3, 4, 5, sorry, 6, 5, 6, 7. All right. So, and in terms of Dmax variable, this includes the max of y-axis value. So there is alert aromatic ring, acceptor donors, low P, molecular weight, polar surface area, and the number of rotator bond. Right. Okay. So we are ready to calculate QED desirability function using these parameters. So in order to calculate QED, we calculate a geometric mean. So we need to multiply each parameters, each desirability score, and actually it is multiply each parameters and divided by the Dmax, and then in the end calculate the geometric mean. Okay, so I define this function to calculate my original QED, and you can calculate by inputting the molecular object in this function like this. So in this case, mole object, the first mole object, QED of these molecules was 0.39, right? So this is the original. This no. This is the customized QED. So I try to compare with the original QED, which can be calculated with RDKit. So RDKit also has a function to calculate QED. So I calculated my QED score and calculated QED using the RDKit's function. And I compared by plotting using a bouquet library like this. Something's wrong or something's wrong. I'm not sure. So something's wrong. So anyways, basically it failed. I'm not sure about that. Basically, yeah, it was almost similar, but I got some error maybe. So in terms of molecular weight, that's okay. Good. Okay. I might be. Yes. Yeah. There was something wrong. So, anyways, so this molecule's QED based on my created function, it is 0.72, and so if I compare to the original QED, which can be calculated by RDKit. So x-axis shows original QED and y-axis shows my QED. So, and the correlation between them is 0.92. So it's not bad. So, and also the difference between original QED and my QED is data set I used, and also software to calculate log P or custom alerts, such kind of things different. So yeah, this is natural. This is makes sense. The difference between the original one and my QED. But so what I want to tell you is that you can create your own desirability score based on this curve fitting So you can select a data set. So today I used just only approved drugs by extracting data set from Campbell with this filtering function. And so for example, we can create your own desirability score about GPCR compounds, GPCR related compounds, and also you can create kinase likeness score by using the data set of kinase inhibitors and modulators. And also in this case, I use the whole approved drugs, so I can extract the recent approved drugs, for example, from 2000 to 2020, and also you can use the old ones from 1940 to 1918, such kind of things. So you can change the data set and create your own desirability score. So I think this workshop, this notebook is very useful to modify and create your own drug likeness or some target likeness score, permeability likeness score, neurology likeness score, such kind of things. So that would be very useful for your future work, I think. So yeah, that's all about my workshop. So okay. Sorry, I think 10 minutes is 10 minutes past. But I'd like to show you my special offer in the end. So okay, good. Oh, this is. Sorry. Oh, I can't show you. This is a video, but I can't show you. Anyways, special offer, I can offer a special offer. Basically, I'm currently running my own membership-based online community named as Infomagician Research Lab. You can access it by clicking this link. So in this community, you can communicate with members in the private chat platform. And also, you can access my Google Cloud notebook collection. Oh, I cannot see. Google Cloud notebook collection and learn how to run AI-driven retrieval synthetic analysis and generative model for de novo design and so on. I actually provide such kind of Google notebook in this community. And you can get free coupons for my online Udemy courses. Actually, I'm teaching some tips on presentation, PowerPoint, and also other free software to create Prezi like zooming presentation and creating the server and the data visualization using Bokeh. But unfortunately, I would say the majority of my current customer is basically Japanese. So these on-demand videos are spoken in Japanese version only, but these are worth, they're worth equivalent to about $900 US dollars. And this information research lab is basically the monthly subscription community. And basically the price is a monthly $29.9 US dollars. But today I'd like to offer the today I give you a discount coupon which is effective forever, even if you cancel the membership. It is monthly $9.9 US, and I just only prepared 10 discount coupons. So this is on first come on first served basis. So yeah, if you're interested in this community, please apply coupon and join us. And also, yeah, if you need to take time to consider, I also prepared $10 per month off, $10 off per month, and this I prepared 100 coupons. So yeah, if you need to take into take consideration more time, so you can use this discount coupon as well. And also, I'm currently giving an affiliate campaign. So if this community members, Information Research Lab members, introduce a friend and he or she joins Information Research Lab, you will receive 20% of the referral purchase price of the monthly subscription plan. And currently 20%, I would say the reward ratio may be changed in the future. So yeah, please access this link. So if you're interested in this community, and this special offer will end on June 13th this year. So yeah, please join us if you're interested in. And yeah, thank you so much for your time. And if you have any questions in the comments, please let me know. And I have a Twitter account, LinkedIn account, and sometimes I use Pinterest, which is interesting. And I have this homepage and this one online school and email address. So please contact me if you have any questions in the comments. Yeah, thanks so much for your time, and yeah, great work. Thanks so much.
Thank you, sir. If participants having any doubts, you can unmute yourself and ask the doubts. Okay. Okay, I request Krupanidhi sir to give the concluding remarks. Yes, sir. He's our professor, sir. Krupanidhi sir. Yes, sir. You go ahead.
Yeah. So, good afternoon to you all.
Oh, good afternoon.
Yeah, Dr. Fuzzy, Hideyashi, and participants. It's a wonderful session that Dr. Fuzzy has taken us to chemoinformatics, wherein he has shown the small molecule database in drug design.
Yep.
He made a start with what is ADME. In this, he has given one of the classical, almost recently classical, Lipinski rule of 5, which came in 1997. So the modification and latest applications from the Lipinski rule of 5 very neatly elucidated by Dr. Fuzzy. And he has made a mention for the first time I heard about QED, quantitative estimate of drug likeliness. And for that, even there are some websites wherein for the drugs of our interest, we can have quantitative estimate of drug likeliness. We have shown through Colab, Google Colab, several chemical parameters, wherein the histograms, at the end he has shown the histograms and the curve fitting of the drugs with various parameters which confirm the QED. Thanks a lot, Dr. Fuzzy. And whenever you come to India, please be at our place for some time. Many thanks. Thank you, one and all.
Yeah, thanks so much. It's my pleasure. Yeah, I hope to visit there. Yeah. India. Yeah, if, you know, COVID-19, yeah, was overcome. Yeah, thanks so much.
It is a nice place. You'll be in contact with Dr. Abraham. He is a dynamic person in our department. He will make all arrangements for you.
Thank you.
I mean, can you share the coupon?
Yeah.
Okay, that's right. That was a really great explanation from Dr. Fuji. So we're glad to have your collaboration, sir. Are you going to share the coupon now, sir?
Yes, sure.
Yeah, fine.
Oh, sorry. This one, I cannot use the chat box. Good. I can use it. So this is coupon for sorry, this is US dollar off month, and this is per month for 10 people.
She's asking for the link, sir. Just check whether what I have provided is correct or not.
And also you can see there is a link in the Google Colab notebook, so you can see below, and you can go to the link by clicking this button. And also there's a coupon code. If you oh, sorry. If this coupon code is not applied, you can use it as well. This is the coupon code, and link is here.
Yes, Dr. Fuji, it's fine.
And the other coupon code. Okay. Okay, thank you so much. Do you have any questions or comments?
No, sir, no. Do you have something to say, Dr. Fuji? Or else I can end the session.
Sorry?
Can I end the session, or do you want something to show?
No.
Yeah. Yes, that's fine. With this kind note, I am going to end this session for today's session. We'll meet on Monday again. Thank you, participants.
Yeah, thank you so much. So if you have any question, please let me know, and you can connect me through LinkedIn, Twitter, such kind of SNS. So yeah, I'm very happy to be connected with you. Thank you.
That's very good. I'm going to end the session now. Don't worry, participants will get the chat box uploaded in the Google Drive. Don't worry, I will send them. Thank you, sir.
Okay, thank you so much.